the Cypress. Sweet. I mean, it's been the best couple of days I spent on a long summer. So yeah, thanks Nicholas for hosting me. It was great to talk to everyone. I haven't stopped talking for a few days. The good places in town. And yeah, I mean, I got to talk about a lot of problems I'm interested in now. I got to talk about problems I was interested in the past. And in general, it was a very fun couple of days. And also thank you, Kathy, for arranging everything. I've been far away and difficult to get in touch with. So since it's a fairly diverse audience, I think my plan was to give you a little bit of a glimpse of a series of problems. I'll spend a bit more time on some of them just to give you a sneak preview into the mathematics. But in principle, I wanted to give you a sample of the type of work I do. And if you're interested in any of it, just talk to me afterwards or feel free to get in touch via email at any point. So the topic I picked, because I think it kind of brings in everything together nicely, is on droplet impact. And I love droplet impact partly because it's a project that lets me work with colleagues doing experiments and colleagues doing a lot of the analytical work, and I usually come in as the more computational arm of the process. So as a broad kind of range of activities, what I tend to do is problems that deal with interfaces. These are problems with drops, bubbles, liquid films, and things like that. And fairly early on, I started also work with industry, kind of on a range of problems in fluid dynamics and outside of it. But the common theme of all of this is I enjoy math modeling, I like scientific computing, and I think there's a good way to use both to one's advantage, not just choose one or the other. So I'm going to stay on the fence most of this talk and argue that it's good to use a combination of the methods, and that's what I'm going to try to convince you. So with that in mind, we're going to start with the bouncing problem. By the way, I'll show you a few sketches. These are all sketches. They're kind of paintings done by a friend of mine back in Romania. So I sent her simulations and she does the artwork for them. So I have a little gallery in my office of like paintings and fluid stuff, which I quite like. But yeah, if we want to think about drop impact, your intuition, what they might tell you is that you have a fairly kind of well-defined range of behaviors. The droplets can either bounce, they can get inside of the pool and kind of coalesce with the liquid underneath, or if you hit it very quickly, it might splash and cause one of these so-called corona-type splashes, like a crown splash, which is very violent. There are other interesting things that you might like. So for example, this works. This is an experiment from the US, and apart from an initial coalescence, you'll see there's a nice little droplet bouncing upwards. And it keeps on bouncing. There's a thin film of gas between them that gets depleted, and at some point, part of it gets into the water, part of it bounces up. And this thing repeats itself for quite a few times. So you get this droplet dancing on the surface, and this is called the coalescence cascade, and it's a nice interplay between a bunch of physical effects. So I think it's, you know, it's an area that has a lot of interesting phenomena. Of course, the water. Actually, I mean, it's water for demo purposes, but in practice, you find that in experiments, water is very difficult to keep clean from surfactants and things. So most people use either ethanol or low viscosity silicone oils, 1 to 5 cents. Yeah, I think that's the gist of it. Cool. And of course, there are a lot of interesting studies at much higher ends as well, where people have studied both, you know, how deep this impacting body can go, what type of stress results afterwards. I think there's a good body of literature, mostly resulting from like the early to mid 2000s, that have established some body of knowledge. And then what's happened in maybe 2015 onwards, we started getting better cameras, better algorithms, and we started advancing the math modeling. And this is really a story about what's happened from 2015 onwards. But just to point out that we're building on a pretty solid foundation there. So here's the team that I've worked with for the first project I'm gonna talk about. The experimental side of the group is over at Brown in the US, in Providence, Rhode Island. So this is Dan Harris, my colleague, and this is his fantastic group of students there. And I also work with Carlos, Galeano-Rios, and Paul Milewski over in Bath. Some of you may know them. So Dan did the experiments. Carlos and Paul did some of the modeling work. I come in doing the numerics, and then we try to find kind of a unifying front for everything. And much of what I'm going to tell you about now appeared in this paper in JFM in 2021 that has quite a bit of the detail. But I wanted to give you just a bit because I thought it's one of the fun ones. So we're going to do all of it. We're going to do experiments, we're going to do models, we're going to do computations. So I'm going to start with experiments. This is how it looks like. So they have a water bath, they'll have a drop generator somewhere, and there's cameras being set up in the far field, and then you follow the impact. So first of all, we're not going to do a liquid drop, but I'm going to get to that next. First, we're going to impact a solid drop. And this is a special solid drop. It's made out of nylon, so think of a plastic type of sphere. And we're going to coat it in a super hydrophobic spray. So think of a fuzzy sphere, so it's kind of cute. And then this is going to hit the liquid bath and bounce. This is what we want to study. And I mentioned this detail because relative to the impact speed and the radius and so on, I mean, they're a pretty gentle regime. But because the droplet is millimetric and the roughness is about 50 microns, this roughness will really be important. And this is what keeps the contact angle quite high as well. So yeah, this is the full setup. You've just seen a bit of the bath before. So there's a camera, the lighting, and the water pump setup. So this is what a typical kind of glimpse to those experiments look like. You get sort of a time series of droplets coming in at different speeds. So here you have a gradient of impact velocities. You see that they go in up to a certain point and then start bouncing back up. And you can argue that, the deeper they go, if they start going up, surface tension makes them go higher up again. So if you want to see a movie of the process in action, this is what it looks like. Slow, medium, large velocity. And then you see that the deformation is quite significant for the higher speed impact one, but also the restorative energy is also quite strong afterwards. It's almost like a spring, and we're going to come back to that analogy later. But this is just for your intuition and to also see the fuzziness of the spheres as part of the process. Cool. So we want to understand a bit of this, and to do so, we need to quantify a bunch of things. And in particular, the parameters of interest in this class of problems tend to be around the amount of time that the sphere is in contact with the pool, the penetration depth, or how deep it goes inside of the pool, and then how much it bounces back up is given by the so-called coefficient of restitution, which is just code for is the exit velocity divided by the entry velocity with a minus sign to account for the fact that one's negative, one's positive. So just think of it as a ratio of the velocities coming in. So, I mean, this is usually, if I show this in a workshop with students, I try to test their intuitions and tell them to have a think. If we have, for example, droplets of different sizes or different densities, what do you think happens with these three metrics? What do you think happens with contact time? What do you think happens with penetration depth and so on? And some of them are not as intuitive. So for example, contact time has a minimum in the middle of the parameter range that I wouldn't necessarily have expected as part of the result. But by contrast, some of the other ones are much more obvious. So for example, the denser the drop, the higher the coefficient of restitution type of situation. So it's just to give you a sense of what the raw experimental data looks like. And of course, this is also the penetration depth. So the higher the speed, or the denser the drop, or the bigger the drop, the deeper it goes. That's, I think, the most intuitive one of the three in some sense. So this is what we really want to understand. And to do so, we're going to try to come up with an efficient model that we can run quickly because we want a mechanistic understanding of the process. And so every problem that we do in applied math has a list of sins. This is the list of sins for this problem. We're going to think of it as a 3D problem, but solve it axisymmetrically. We're going to assume that it's a big enough domain so that waves don't come back. It's a deep enough domain so that the bottom doesn't matter. And in general, and I think this is the important point, we're going to consider a linearized version of the problem because this is what's going to make it quick. But at the same time, we have to admit that it only counts for small deformations. So it's only going to be valid up to a point, and we have to respect that fact. And the usual questions I like to ask is, well, how small is small? And that's why we need the computations as well later. So this is also kind of built from earlier deformation theory from kind of larger scale objects. There's a history for this problem in terms of all sorts of projectile type things and so on, and how they hit water. But by and large, you have to consider that the important things here are we don't know the contact area, and we don't know what to say about pressure between the two of them, and the coupling between the sphere and the liquid is obviously the most delicate and the most important part of the process. So with that in mind, I don't want to start with equations. It's Tuesday afternoon, I think it's time. So this is what the typical system looks like. If you take those assumptions into account, then with a bit of notation, we get a velocity potential, and eta is for the free surface elevation. So you get a Laplace equation for what's happening inside the pool, and you get a series of conditions that are typical of the force balances on the interface and the usual type of conditions you get there. The reason I flagged this is that if you want to do a bit of analysis, you realize that actually this term is one of the key terms coupling what's happening inside of the pool with what's happening on the surface. So what you can do is build one of these Dirichlet to Neumann maps on the basis of it. And then what ends up is you can do it with one of these principal value of the singular integrals, and you get a very nice kind of compact form of this equation, which I'll show you in a second.
So what is eta?
The free surface. Yeah, it's just the surface of the pool. So
The velocity of the surface.
the shape of the surface.
Eta d?
Eta d is how the shape of the surface deforms as a function of time. So as the droplet comes in, it measures the change in how the surface deflects. Whereas phi measures is the velocity potential inside of the entire pool. So eta is a surface quantity, phi is a below surface quantity.
Phi z
Is the derivative with respect to depth inside of the fluid.
It's a surface integral, right? You have a surface integral. So what is the surface integral
Over the entire surface of the bath. So the bath is,
Why are you interested in the entire surface of the bath?
well, because it decays at infinity, you actually end up only having contributions near the impact site. So it's a mathematical formalism essentially to allow nice boundary conditions. Of course, as it decays sufficiently far away from the region of interest, it will contribute with zero and you no longer care about it. And when you compute it, you solve it on a finite grid, and again, you don't care about the infinity part.
And the epsilon appears in the denominator, your epsilon.
Where?
Epsilon, the limit
Yeah.
appears in the denominator of that expression.
Ah, you mean here?
Yeah.
Yeah, because you have to take it from a certain direction. So because information exists from the pool upwards, for example, then you're only allowed to take limits from a given direction. Basically, one of the things that maybe I haven't put on my list of assumptions is that we're also neglecting air as part of the problem. So for example, there's no gas information coming in. You only model the liquid pool. So then you basically have to take all these limits in the spirit of small deformations on the one hand and limited information from the gas phase on the other as well. So combo.
You would consider gravity.
Gravity is part of the problem, yeah. Gravity comes in through the Froude number contribution here, which is GL over U squared, or yeah. Oh, yeah, this one. V squared over GL. Yeah. And in this case, I mean, formally, we can fit this integral as being a ball. So effectively, that limit really comes in out of how we formulated integral in the Neumann map. So I think it's more connected to how we summarize all of this into one formula, as opposed to having to resolve the entire set of PDEs all across the surface and all across the surface.
So it's not obvious how that formula.
To be fair, I am hiding about 2 or 3 pages of analysis in this. That's why I mentioned it's more of a kind of whistle-stop tour as opposed to the full detail. But the couple of papers that are buried under this are pretty explicit. And actually, even the act of resolving this integral requires an adaptive mesh and some careful treatment. So it's, yeah, in some sense, please do not feel bad if it's not obvious. It may completely not be, but it's my job to try to help. Sweet. So with this in mind, I mean, that top bit that I repeated here tells you what happens with the liquid pool, and this bottom bit that I brought in tells you what happens with the impactor, with the sphere. And it's pretty classical Newtonian mechanics. It's a force balance argument. You have a few extra conditions. So if you remember, that sphere was hydrophobic. So we're going to assume that the region has a 180-degree contact angle. So they never touch in this simplification. And also that the pressure, for example, is 0 outside of the contact region. So really what we want to estimate is how much of the region is in contact and what is the pressure profile underneath. And to do so, the coupling is done by these terms. So really when you solve all of this, this is the term that contributes to the pressure from the Bach equations, and this is the term that you integrate over the contact region, so over the region that you want to solve, in order to get what is the effect of the pressure coming in from the liquid. So sphere wants to go down, water wants to push it up, and really this equation expresses the balance with the suitable set of boundary conditions. All good?
So there is no effect of the thickness.
No.
Thickness is,
Yeah, we consider it to be sufficiently, let's say, innocent in this case not to affect. Yeah, it's a deep pool, effectively. So.
Where the assumption of hash supercategory is the real candidate, they don't have it.
Effectively, it's through the continuation of this line.
So what if we get the code angle as
We decided at some point that we want to sell this as a parameter-free model. So in this sense, because of course you can either not coat the sphere or coat it with a very specific contact angle, and it becomes an extra parameter in your problem. And I think we wanted to operate, even though I realize it's a bit, it already has quite a bit behind it, we wanted the simplest possible regime to characterize, and we thought of going to the most super hydrophobic limit we could achieve. So yeah, this was essentially trying to make this part of the process as simple as possible to model.
But in reality, when you compare with experiments, this is a big approximation.
If the contact angle in the experiments is above maybe 120, 130 degrees, the approximation holds really well. You also have to take into account that the model is built for pretty small deformations, so I think its range of validity has a few limits anyway, that we'll see in a second.
Yeah, the biggest assumption is the small deformation.
Exactly.
Because it's not normal.
Yeah, precisely. So maybe that's a good time to come in to tell you what we do about bigger deformations. And I'm going to present the DNS part of the process. So we're maybe about 10 years now, and it's also, I guess, part of the reason why I'm here. I've worked with Jerris and Basilisk, and I know Nikos, Andreas, Yanis have a bit of work with it as well now. This is a code that's built for PDE problems. It can do a bunch of other things, not only fluids. The reason it's well liked in the community, apart from it being open source and having a good user base, is it's got adaptive mesh refinement. It's got pretty decent parallelization capabilities. And in general, it's quite efficient for the type of problems that are difficult to resolve in commercial packages. It's built towards good fundamental science in quite a precise way. And this is, one of these examples where you can get it to work for a nice problem. So the equations it solves under the hood are now the Navier-Stokes equations, non-simplified versions, so with all the nonlinearities in them for both fluids. So for the liquid inside of the pool and for the gas outside of it. So no more ignoring the gas. And the way you transition from one to another, you do so with the so-called color function, which if you want to have density 1 in one fluid and density 2 on another fluid, you create this symbolic function in the background, call it C. And when C is 1, this term is 0. When C is 0, this term becomes active and this one dies. So effectively, you have, maybe if I return to this one, it's a nice way to explain it. When you're inside one of the phases, this function is 1. When you're outside of it, it's 0. And cells cut by an interface are a value between 0 and 1. And this gives you information about how to build normals, curvature, and in general, how to build the fluid interface on top of the grid. And you have to, of course, transport this color function with you. So this is nice because you don't simplify much. It's expensive, though. This is kind of orders of magnitude more complicated than the model we resolve. And I think this is part of what we want to retain in the story.
Can I ask something? You don't use the second equation shown here, right?
No,
So
not directly. Exactly, yeah. It's a useful explanatory mechanism. But otherwise, yeah, you only solve it.
So when you say expensive, can you tell us what you mean?
Yep. So this is a typical grid where I've refined with respect to interface shape location, and we refine with respect to velocity changes and vorticity changes. Even with all this adaptivity, it requires maybe 10 to the 5 cells. And with respect to runtime, it needs maybe 40, 50 CPU hours. The model can be resolved in 3 seconds.
Nothing.
It's nothing for this particular problem, but it's still 4 orders of magnitude or more relative to the model. So for example, if I want to explore one instance of this formulation, I already have 40, 50 hours easily kind of leave that under my laptop if I need to. But if I want to send 400 of these computations or 1,000 of these computations, then I need a bit more. And also noting that this is axisymmetric, for other problems kind of later on in the presentation, we may not have the luxury of doing that axisymmetrically. So I think kind of of magnitude or more or less. But you still have to pay a price because you have to resolve the thin gas region between them, which was interesting, but you have to put it still in a pretty big domain because you still want to minimize reflections and so on. So your smallest scale is at the order of microns, your largest scale is at the order of about 10 centimeters. So for that, you need to pay a price because with this multi-scaledness, you have restrictions in spatial resolution and in temporal resolution by the CFL number. So the reason why these are expensive is not actually because they have a certain number of degrees of freedom, it's rather that you have to evolve those equations hundreds and hundreds of thousands of times. And that's because it's a rather stiff problem. And I can make it worse. So for example, because you don't have a natural fluid structure interaction mechanism, the one approximation I am making is that rather than having a solid here, I'm modeling this solid as a highly viscous, large surface tension coefficient fluid phase, which is basically saying I'm not going to let it deform, I'm going to keep it as close as possible, but I still have to incur a penalty because the contrast between the physical properties of the drop and the air is considerable. So as soon as you have more than a 20-to-1 viscosity ratio, the problem becomes quite stiff and difficult to resolve. And in this problem, it becomes about 1,000 to 1. And you have a choice at some point. Do you want to stick to this type of algorithm, or do you want to use an unstructured mesh and a real kind of interface tracking one? But each of them has kind of deficiencies. So at some point, you swallow the pill, and then you decide which route to go through with.
So just to understand, these contours that you see in the blue,
Yep.
What is this? I mean, you said there is no air, so what is
So the computational model, the full direct numerical simulation, solves everything, including the gas. Yes. The model, the reduced model that I showed you before, the one that only allows small deformations as well, that one doesn't resolve the gas.
So this is extended.
This is pretty much as few simplifications as possible, and the model is as many simplifications as possible because we want to use one tool to inform the other in an efficient way. In some sense, if we make a simulation that's too approximated and a model that's too good, they lose their ability to inform one another. I think that's the key part of the process. So we want to keep the model as fast, but still reasonably reliable, and then to push it further with the simulations where we don't have any approximations. Because
So when you say inform, what exactly is it?
it's a validation technique, if nothing else. So when you do this type of simulation, you can either rely on achieving mesh independence, which is a good thing to have. You can compare to experimental results, but realistically speaking, because of imaging restrictions and how much you can visualize, you cannot get a lot of information out of the experiment beyond trajectories, but you can get some out of the model. And if you work within the parameter range where the model is valid for small deformations, then you can use it to test whether your simulations are doing the right thing. And conversely, you can feed information about, say, the pressure inside this gas region to inform a good approximation for the model. So I think the key point is to try to share as much of the solution between them to improve both at the same time.
No, sorry, please.
So that was a pressure contrast, right? For the blue.
So everything you see here is just colored in terms of the fluid phases. It's just dark red to denote the drop, lighter red to denote the pool, and a blue for the air. There's no other information in here apart from identifying the different.
The shading are
Oh, it's because it's
yes.
The shading is the grid.
Yes.
Yeah, it's showing you the adaptive grid. I see. Yeah. So it's showing you that the region that's most refined is the contact region that we're aiming to resolve the bigger part of the problem. And then sufficiently far away, we don't need as many grid points because the information becomes more and more, less and less useful as you move away. So then we don't allocate resources there.
So Radu, sorry, just for me to understand. So in the continuous scale, you have two different fluids or phases.
Yep.
The interaction between them is described via with parameters.
So in terms of what happens at the free surfaces and how these fluids talk to one another, you've got 5 conditions. So you've got continuity of velocities. So across this interface, basically radial velocities and vertical velocities are continuous. That's 2. You've got a normal stress balance, which also includes the surface tension part of the process.
That's fine, yeah, but I mean the interaction between them is just via surface tension or?
So you have the normal stress balance, the tangential stress balance, and the kinematic condition, theoretically speaking. And I think all of these coupled together bring you the information, because you can't really kind of take the pressure or the surface tension or the velocities like individually out of the system. So it's a fully interactive one where surface tension definitely has a role to play, and physically, depending on where you are in the time evolution, so as the drop sinks, inertia will play more of a role, and you get more information from essentially velocities and viscosity dissipating the energy, and on its way up, you get more of an influence from surface tension restoration forces, but ultimately, it's all a coupled mechanism.
How do you get the values of surface tension?
No, I mean, we specify a constant value for surface tension, a bulk quantity, which is, the surface tension between water and air in this particular case.
But you don't have only water, sorry, I understand. So you have water and another thing, that is silicon or whatever.
You mean the A vector, the body. Oh, this one, we just model it to a high enough value so that the droplet doesn't deform. I mean, I can tell you the exact value, it's about 15 times as much as the water-air one. But effectively, what I want from the A vector from the sphere is that so it doesn't deform, we just want to impose a sufficiently high value to achieve that goal. So that's not physical in terms of setup. But the surface tension coefficient between the pool and the gases, it's just
Between the water and the air, that's
yeah.
clear. Okay.
Yeah.
I was wondering more about the interaction between the solid and the liquid.
Because they have an entrapped gas region between them at all times, you never break that one. So you never have the top red bit with the bottom red bit touching it. You keep this compressed region that's quite high pressure, and that's the mechanism through which kind of energy is transferred between the vector and the pool.
Would you be able to solve this one if you had a solid for the drop?
I haven't seen yet. So you can use a moving solid component in Basilisk if you have a prescribed motion, so you can translate something at a given velocity. But I haven't seen a good approximation that's a true fluid structure interaction model, which can actually respond to what the fluid is doing. Mostly because you have the contour cutting through cells, it becomes quite a difficult problem to solve, and you have all sorts of issues maybe with wetting and contact lines coming up as well. I think it's one of the outstanding problems in the area. If you were to use finite elements in an unstructured grid, where then your interface becomes a boundary of the problem and you can impose things more elegantly on it, that's one way to go. But then what you lose is all the good things that BOF offers you. So you have to make it right. Yeah.
So I mean, I was wondering about the BOF. Is it like a pseudo BOF therefore does it impose, because I'm not familiar with the BOF, does it impose internally boundary conditions? Or you're familiar with it?
No, so what tends to happen is at each step, you have basically, you inherit everything from the previous time step, velocities, pressure, position of the interface. And then as you resolve this, you make progressive approximations. So you start with fractional approximations for the velocity fields, they boil down to auxiliary values for pressure. So what you do is advance everything, fractionally to begin with, and then you drag everything else with you. And what happens is that once this implicit function, the color function, moves, then it gives you enough information to rebuild the interface at the next stage. So it's what's called an interface capturing technique, because rather than keeping track of explicit points on the interface, you keep track of the background color function and you rebuild the interface at every step. As opposed to interface tracking techniques, which you pretty much put a bunch of marker points and you embed those and you remesh.
Yeah, I was just basically there's two variations of both methods. The ones that basically
This is what's called CLSVOF, so it's level set enhanced. If you're familiar with it, it uses information to kind of rebuild the curvature component if you want to distinguish between the two classes.
Yeah, okay.
And keep the interface thickness manageable.
Yeah, exactly. I think all of this ideally should happen such that your interface is always, like the variation in the color function develops over 2 grid cells, 3 grid cells maybe. But of course, there's ways to kind of extend that formulation. Sweet. I may have been a bit ambitious, by the way, in terms of how much I put in this presentation, but you guys are a good bunch and you ask questions like most other people. So I'm very happy with that, but it does mean I'll probably need to cut a few things, but that's absolutely fine. Because I'm happy to talk for as long as possible, but I'm not sure I want to keep you after 5 p.m. So I'm going to leave some decisions with you later in the talk. Like Sweet.
it's a bouncing problem.
It is a bouncing problem indeed. Okay, so let's see how these things do. We spent a bit of time. I think we understand at least part of the processes. If we now start putting things together, with all of these approximations on all sides, what are we actually getting out of it? So these are experiments. KM stands for kinematic model. That's the mathematical model I presented, and the DNS are the simulations. And you see, you get a reasonably good qualitative agreement, but there are still, some regions of not perfect agreement. So we want to understand what is going on. And I mentioned, first of all, we can look at trajectories. Like this is what I started to show you from experiments. And the three different approaches are the three different sets of symbols. Ultimately, it doesn't really matter what's what. What I wanted to get out of this is that for a moderate velocity, whereas you have generally good agreement, it's not quite perfect. By contrast, if I show you what happens, so this is a much smaller velocity, and I'm only showing you DNS and model here, the overlap is almost perfect. So if you operate for small enough impact velocities and small enough deformations, you can get that type of agreement I mentioned to kind of cross-validate the model and the simulation. But the model can't do the high-speed impact velocities, and the experiment cannot visualize the deformations at this level because it's such a small deformation that the cameras don't capture the result. So that's why you need all three of them in some sense, because they can complement one another.
But that's relative to the depth, or is it just if you have less deformation, then you will get less of an error?
Yeah, but I mean, so the type of deformation we have here is, at the level of a fraction of a micron, a fraction of a millimeter type of situation. So depending on how you set up your camera system and so on, you just can't.
No, I mean between the model and the DNS.
Yeah. So what was the question again?
So I mean, you said for larger velocities,
yeah,
you get more of an error.
Yep, like
larger errors.
This type of picture. So what tends to happen is that the DNS tends to have a slightly stronger bounce, whereas the model has a kind of a different time scale in the relaxation process. It takes a bit longer for it to readapt itself. But we're still talking reasonable amounts of error. It was just some of the simplifications you make along the way with the model start showing signs that they're getting tired.
Can this be related to the 2D nature? Because can the energy escape in the third direction? Maybe things are more energetic in the 2D simulations than proper 3D simulations.
But they're actually symmetric. I mean, you retain RZ variation. I think the only time where that would play a role is, for example, if you accidentally misalign your droplet coming in and comes in slightly obliquely, then you get an anisotropy in how the information gets started. So for this, in principle, it should be all right. I think the axis symmetry is not a bad approximation in itself. But I do think the fact that you're linearizing it is making it kind of more problematic than it should be. Yeah. Cool. So these are contact time, coefficient of restitution, and depth for all of the parameters we tested. Different densities, different drop radii. This is kind of the master diagram that puts everything together. And the experiments are the wide bands, the symbols, the diamonds are the numerics, and there are a few crosses in there, and those crosses are the model. And what you can realize is that there's relatively few crosses in that picture because the model is only valid for a relatively small amount of velocities. So, on the one hand, we can be quite happy in some sense. There is a good agreement in the techniques, and there's good predictive capabilities in the computational side. On the other hand, there's still a few phenomena that you may see. So, for example, maybe it's most visible here. There's a clear kind of gap between the symbols and the experimental results. And that's, for example, where that approximation of when you coat your sphere with that superhydrophobic spray is not perfectly superhydrophobic. And basically that fuzziness, since the gap in the experiments, the air gap is actually quite a bit larger than in the simulations, that's when you get that slight difference in the story. So we've attempted to explain as much of this picture as possible. Ultimately, we were quite happy because what you can do once you have something like this is, even if experimentally you can't reach a certain range, you can then extend it computationally in one direction and with a model in a different direction. And then you can start bringing in some of the big guns in terms of explaining things. So for example, you can now start thinking of this system. If you remember, I mentioned the spring analogy. If for those of you who do these capillary type flows and you know the Young-Laplace equation, if you think of how surface tension interacts with everything, then you can squeeze out the right scales to this problem and collapse all of the, for example, this is the penetration depth, into one master graph that pretty much brings all the data together. And this is nice because now you start seeing a lot of the crosses from the model. And the thing is, the DNS and the experiments can't reach that low, but it takes you all the way to the bottom limit. And then, of course, the model can't reach higher than that, but you can use the other methods to get that far. So for the quantities of interest, you can then kind of collapse everything into one set of results. And then for any future combinations of liquids and so on, then you can get this type of master curve to use for predictions of how deep it will go, how much it will bounce back up, and things like that. So that's kind of one of the key results from this side. I may do, well, let me show you a fun one. This is what we called resurrection. So once you have that master figure, you can start having fun exploring interesting phenomena. I want you to pay attention to this one. And what happens is it gets submerged, but then it still has enough upward momentum to pierce through the liquid interface. And now it starts bouncing back up. So basically you get the situation in which, I'll play it again because it's kind of fun. This is just a slightly smaller velocity, and here the liquid bridge doesn't quite close and it just bounces back up. But here it does close, however, it's lucky enough to still keep moving upwards. And the difference in density between the sphere and the pool is not particularly high. It's 1.2 as a factor, so that's why I can do this.
I find it very miraculous. I mean, it almost stopped.
Yeah.
What is the energy? From where does it get the energy?
So now follow the south pole, and you see that before this liquid bridge closes, this is starting to move back up already, and only now. So that's the trick. Like basically, it has enough of an impulse going up. Yeah,
Just to reach the
yeah.
that place.
That's also part of the process. I think you have to take into account that this is really a battle between gravity and anything that can give you upward movement to fight against gravity. And in this case, the fact that the interface closes a bit sooner gives you a bit of an early push. And then once you hit the surface, even the mechanisms like you mentioned, like to get through the interface, you need to jump.
Yeah.
I will not have guessed. I would have guessed that it stops.
We are dealing with phenomena in the small.
So densities are more or less the same.
Yeah, it's 1,200 kilograms per meter cubed, and water is 998 or something like that. Yeah. And I'm stubborn, and you can do this numerically as well. So if you search for it, if you know that that phenomenon exists, I'll show you the equivalent numerical picture. So this is, you'll see the different velocities. I would have never done simulations that are so close in velocities to one another had I not known. So here you see a place where the interface doesn't close. Here the interface will close, but it's gone so deep that even if it moves slightly upwards, it won't be rescued. This will stay sunk and eventually it will go all the way down. But this one, given enough time and patience, and I might speed this up a bit in the interest of your time as well. You see that if you follow the liquid bridge here, it just about pierces through.
So where is the energy comes from the water?
The energy?
Yeah.
No, it just simply comes from the fact that it was preset to move upwards. So it started sinking. Maybe follow it again. Let's play the game. So it sinks.
Yes.
And at some point, it'll start moving back up because the surface, it tries to close and it almost manages, but already, if you see it, it's moving upwards. And this initial velocity, although it's small compared to the velocity that it entered with, because it's such a small density difference, it's enough to take it all the way back. It doesn't need much of a push because it's a pretty small sphere and a pretty small region to cover. So I think it's just, if you think of it as once it's already submerged, just send it back up with a small velocity. And if the density difference is not sufficiently high, then you can just go through.
It just stops. So I don't understand it. The energy there, and understand.
It's slowly moving upwards.
It is.
Yeah, if you monitor the velocity, actually maybe I can just show you, and I guess I'll get to your question in a sec. So these plots here show you the trajectory of the south pole, for example, of the droplet. I don't remember if it's the center of mass, but either way, if you follow the red line, which is the resurrection case, once it hits its minimum, it goes up in a way, and this acceleration of it going up is when it breaks this liquid bridge, because then surface tension tries to make it more efficient and it kind of squeezes it back out. So really, what you wanted to do is to make sure that the distance between this point and the point where it breaks the interface can be covered by that upward movement that is given. So it's a pretty exotic mode. That's why we kind of had a bit of fun with it. But it's one of the fun ones that, had I not known it was there, I would have never searched for it. So that's where the kind of mixing of approaches comes in. Hit me.
I saw a tiny droplet
Yes.
fly or up into.
Yes.
Is that real?
I mean, we haven't compared that part. You do see droplets shooting up on occasion because it's a similar phenomenon to how when bubbles burst and so on, you get the Worthington jet style of dynamics where a jet forms and bubbles, droplets shoot off. So from conservation of mass perspectives, it should be there, but it's a phenomenon that is quite kind of delicate on top of the droplets. So we haven't quite looked into it.
Boundary conditions at the sites.
I kept them as kind of free slip. So there are no penetration to preserve mass inside, and they're allowed free slip and a 90-degree contact angle. So of course, because we set them to be something like 20 radii away, if you wait enough time, the propagating waves will come back to you if you wait long enough. But
so you didn't dump.
No, we didn't dump anyway. We can if we need to. But I think the purpose was to only study one bounce, and then even if they do come back, they don't affect the main metrics that we were following.
If you have a smaller enough container, then the waves coming back could actually sink you. Or
it's one of the things we're going to study next. If we kind of modify the confinement effects. Okay, so then in that case, I have a question for you. We can do one of three things. I can tell you about the liquid version of this, and I'll show you the spoiler. So, whoops. If I go here, you're already warmed up for this one, so it might be quick. But now instead of putting a fuzzy sphere, which has this complication, we have a droplet that does deform, and it makes things a lot cleaner. I can tell you about a nice splashing problem, which higher speed impact and crown splashing. Splashing, okay. Well, if I had gone through the splashing, the third option would have been, do you want me to tell you what I do with industrial particles with that problem? Okay, let's go with the splashing and see. Excellent. Okay, splashing it is. So I'll tell you how I got into this problem, which does involve a bit of industry story, and then I can tell you who I interested later after the talk. I was working on my microfluidics stuff, and maybe it was 6 months before I was supposed to finish my PhD, and I got a great news that we got a new grant in the department, and I had the opportunity to work on it, and I gladly accepted, and then I found out that we had one of these big quarterly review meetings with grant funders 2 weeks later, and then I also found out that the grant started 3 months ago. So that was a very rapid introduction to droplet that I had to do, pretty much drop everything else and go. And the other thing I wanted to know is that from the perspective of kind of the fundamental part of the process, this is a beautiful problem. Like it has 150 years worth of history. Back in the day, like the first study for this, which came from Warwick, what they used to do, because you have to take into account these were the early days of photography, you go into a dark room and you don't just study a droplet falling, but you take a droplet and a marble and drop them at the same time. And as the marble touches the surface, it generates sparks. And those sparks, like it lights up the room in such a way that with early photographic devices, you can take images that look kind of like that or sketch them. So, people were interested in this, and this is the modern realization of that experiment. And you can see there's quite a few differences in terms of finger formation and so on that people attributed to kind of contamination of the kind of early stage equipment and things like that. But what I want to tell you is that people have been interested in this problem for a while, and I got into it because of aerospace applications, but people also are interested because of inkjet printing, because of pesticide distribution, so there are a lot of problems. And going back to like the early 2000s, what's nice about this problem is, well, there are a lot of parameters to study. We're going to try to keep it quite clean, but take into account that we have densities, viscosities, surface tension, Newtonian, non-Newtonian, gas, no gas, all sorts of things. What type of surface do you impact? So kind of in an extension of my bouncing problems. We're going to now go to the higher speed impact, the splashing problems. And this is work I do with my colleague Matt Moore, who was in Oxford at the time and is now in Hull. And this is a completely different world. So in some sense, I want you to keep the experience from the last half hour, but start a new blank sheet with a completely different set of assumptions, in which now, the quick version of this is to pretty much say that we throw in everything away except inertia. So no surface tension, no viscosity, no gas, nothing but inertia and the shape of the interface. And we're going to study from the perspective of wanting to understand if droplets hit one another and they have different radii or velocities. How does this work? So first of all, we need a mathematical model for this. And this one comes from so-called Wagner theory. Anyone heard of Wagner theory here? It's a 1920s, 1930s theory. It came up because of problems in planes landing on water or ships landing. And they wanted to understand the forces of the bodies hitting water at high speeds. And it's a matched asymptotic analysis framework. And what it does is it considers the geometrical structure as having been formed. So basically, the droplets have hit one another and they form a jet between them that will result in the splash. The outer region of the matched asymptotics part will give you the shape. The inner region here will give you the root of the jet and the geometry part of the problem. And then you have a thin, long region called the jet region that gives you information along this structure here. And it's nice because each of these regions has a different type of mathematics behind them. So I'll give you kind of a quick version of each if you want to see the one slider. But basically, it's asymptotic analysis, it's complex analysis, and it's PDs that all kind of contribute to this. So if I go to the outer region and make those approximations, I need to solve Laplace equations in each of the two fluids. And what I get is basically a moving contact point between them. That's the root of the jet that's moving outwards as the droplets hit one another. So you have to imagine that that moving point coincides with this region on the map. But because it's just a point and because you have a particular type of singularity there, well, it breaks down. And that's where the asymptotics come in. You need to go to the next order and jump into a new region. And that's the so-called inner region. And it's governed by these types of free surface flows or Helmholtz flows. So this is the jet that you were describing before. So if you move into a suitable frame of coordinates, then you can solve this problem and you can get information about the thickness of the jet or the velocity in this space of how this region is moving. And then you still have a missing piece. You don't know what happens afterwards and you need to close the problem. So you jump again and you go into the third region and you move into a suitable frame of coordinates, so along the jet. And what you get is pretty much shallow water equations. So it's a nice set of PDEs. We know how to solve them. Method of characteristics comes to mind. You get nice solutions for velocity and thickness along the jet. And I emphasize that these are closed formulae for all of them. So what you have to imagine as a summary is what the analytical framework gives you is the location, the velocity, the thickness of this jet. But they're all done in this, again, approximate framework in which you've thrown away surface tension, viscosity, and a whole bunch of things. So is it any good? And what we're going to do is compare it to simulations done in Basilisk, which give you a similar picture, but now, I'll stop it at some point, you have all the effects still in. You have surface tension, you resolve for the gas again, bubbles forming and so on. You have capillary tips forming, but what we're really interested in is the properties in this region. So I'll tell you a bit about the comparison. This is how long these take. So we're talking about 1 million cells per calculation, about 1,000 CPU hours in total. So not huge, an order of magnitude increase, but they generate a lot of data because we want to compare information everywhere in the domain pretty much in order to kind of evolve the jets around. Analytically, I told it to you in 3 slides. It's about 60 pages of analysis. So math usually kills me when I get this version of the talk, because that's a lot of hard work that went into it, and it took our PhD student maybe a couple of years to get to that stage of resolving the same thing. So, but it's really fun, and Matt's an expert in it. The only downside is, this was math when the project started and when you finished. So, you go into proper philosopher mode. I like to say it's not working with me, but you never know. So yeah, with that in mind, here are the comparisons. Symbols are the numerics and the lines are the analytical prediction. And I didn't perhaps emphasize that it's an early time asymptotic theory, so you only expect it to be valid at a certain point. Without necessarily kind of going through all the detail, what I want to emphasize is that the agreement is actually pretty good. So we're quite happy as long as we stick to early times. That's the jet location. This is the velocity along the jet on the bottom right-hand side. And of course, you know, the analysis predicts a certain behavior, and you have to make adjustments. Like, for example, there's no surface tension, so there's no capillary tip. So you don't expect these bands in the analysis, but you get them in the computations. But by and large, you get some pretty good information out of it. And same for the thickness along the jet. So the real idea here is how long can we trust the Buckner theory results for, and then can we use them to see better initial conditions in larger scale calculations later. So very quickly, I'll just note that if we move to the 3D problem, we're now experts in it, so I don't really have to go through the same set of assumptions and so on. But basically, just imagine the generalization to this problem. And if I just show you the results, which are over here, these are the 2D results we've gone through, and the 3D results are extensions of these formulae that take the geometry into account. So the whole point here is that once you do the heavy work in 2D, going into 3D is not that difficult. And if you want some intuition about what these problems look like, this is not the type of problem we resolve. So we're having droplets that hit one another and generate these splash sheets, which is what the analysis studies. But then we got a lot richer effects in terms of splashing, in terms of drop generation. So now we jump another order of magnitude, and these are tens of millions of grid cells and a lot more computational runtime. So yeah, we're interested kind of in taking it all the way up to 3D. Now, part of me wants to stop here, but I'll just note that there are a bunch of things that I can tell you about. If you're interested in either how we apply this in industry with companies in aerospace or pesticides, I can tell you. And there's also model upgrades that you can do. So basically, now that you know all of this, you can re-include surface tension and viscosity in here. But I realize it's 5 o'clock and I should stop. So what I'll do is I'll just want to mention where I see this going in the long term, which is what I really want to do with this type of work is kind of work in a framework in which you use the simulations in a kind of small space where they're valid and you can get very detailed information, but then transition to other methodology spaces where you can really achieve a multi-scale type of process. And then you get to adopt simulation data, you get to adopt PD theory and kind of probabilistic approaches, but then you also go to things like particle models and so on that get to send those secondary droplets that you saw ejected sufficiently far away. So really the idea is to put everything together in the context of certain kind of practicalities. So with that in mind, I mean, I told you about a bunch of work that happened over 7 years with 3 different institutions. So I burned a lot of core time through them. So I think there was a massive thank you. Again, thank you for listening.
Thank you, was fascinating. I want to ask about the bubbles in the jet. Since it because of communication pressure and you get bubbles, I'm sure that's something like a.
Which problem? The splashing
The
one?
last one, what the jet is coming out.
Yeah. So let me jump to it because I think it's simpler. Do we mean? No, not this one. So for these types of movies?
No, before when we did
The
one
2D
was
The
before
2D one.
The 2D one. Okay, cool. I'll go to the 2D one. Yeah. This one?
Mm-hmm.
Okay.
Yes, the bubbles.
Yeah, with you now. What's the question?
This is something that